Hi class, we are on chapter 5.2 today. We're discussing linear models once again, but instead of initial values, today we're going to discuss boundary values. So these are boundary value problems. So again, we're just going to kind of derive some equations and talk about them and how they're used. The first thing we're going to talk about is the deflection of a beam. So let's say that we have a function, let's call it m, be the bending moment at a point x along a uniform beam's axis of symmetry. So what we're talking about here is that if we were to take cross sections of a support beam or a rod, that each cross section is the same. That doesn't necessarily mean that it's all made of only one material. This beam could be made of multiple materials, but if you take cross sections of the beam, they're all uniform. They're all the same. Okay. We're going to let y of x be the amount of deflection from the axis of symmetry. So again, if we're setting the beam up and down, the axis of symmetry is the up and down axis. Okay. So here what we're going to do is at any point along that line, we're going to look at how far our beam bends away from what would be its standard up and down or left to right position. Okay. So our model here for y of x is going to basically be the curve that is in our beam that is due to stress. Wx is going to be the load per unit length. So this is going to be for every inch squared, for every centimeter squared, for every foot squared, how much weight or load we have on our beam. Okay, so this is going to give us an equation. So these things are related, that the second derivative of our bending moment is equal to the load per unit length. Okay, so we also have this equation. Okay, so if we take m in its regular form, that is equal to EI times kappa. Okay, this is the Greek letter kappa, not K. E is Young's modulus of elasticity, so it's the elasticityness of the material that we're working with, right? How much does it tend to bend? There's a directory that you can look up for different materials for their elasticity value, modulus. This is, you don't have to worry about this, you won't have to look this up, but in practice you would go somewhere and find that value, right? I is the moment of inertia. You're not going to be asked to calculate this either, but you could. This is a very kind of standard thing that you talk about all the way from in physics and in engineering, also in like pre-calculus and calculus, right? But you won't have to find this either. So don't worry about these things. They're just going to pop up as fixed variables. Okay. So this EI value is called the flexural rigidity. Okay. It's basically how flexible is your material. Okay. Kappa is the curvature. You should have learned this in Calculus 3. In Calculus 3, we talk about curvature a lot. You talk about the tangent vector to a curve in 3 dimensions, the curvature of an object. So it's the same exact formula from your calculus. It's basically the second derivative of our function that talks about the deflection divided by, okay, -3 halves power of 1 plus the first derivative squared. Okay, so I decided to write it like this as a product form, but normally you see this as a rational function, right? So instead I just wrote it in product form. Same thing. This is negative, so this would be under the y double prime. Okay. So when the first derivative is close to 0, okay, this thing will basically go away, or it's negligible. I'm going to get 1 to some power, which means that my kappa, my curvature, is basically just the y double prime. Okay, so that's our assumption. We're going to assume that the first derivative is basically 0, or close to 0, or negligible. So that's going to take this equation that I have here m equals ei times y double prime, because kappa is now pretty much y double prime, and I can differentiate it. Okay, so again, this is the dE that I'm working with. So I'm going to take my m function and differentiate it twice. So m double prime is ei y to the fourth derivative, and that will be equal to be the load per unit function. Okay, so then this is going to be the dE that I'm going to be working with. Okay, so if I want to talk about the deflection of a beam, I have my flexural rigidity, I have my load per unit, and then I'm trying to solve for my y function, which basically tells me the curvature away from the axis of symmetry due to the stress of this load. And again, that should be proportional to basically the structural integrity, the flexural rigidity of my object. Okay, so that's the first equation that we're working with. So I took some images from our book. So again, you guys should be reading before we go over this material, right? I know you can go back and you can look through these videos, but it's always better to read and then watch a video, or to watch a video and then read. But you should definitely be reading. You know, you're going to continue on through school, and you have to, you know, you'll figure out sooner or later that you have to read the textbooks. Like it's just, that's why they're there, right? So I suggest you kind of go through back and read. I'm really just summarizing what the book is doing. So you should definitely go back through and kind of read through that one more time, just to get a little bit deeper understanding of what's going on. But we have different boundary conditions for a beam, right? So here our beam looks more like a wire, which is fine, okay? But this is just to summarize what kind of applies to everything. So I can have my beam kind of fixed at both ends, right? So at my initial end and at my terminal end. I can have it fixed at one end and free at the other. Okay, this one is called a cantilever. Or I can have it simply supported or hinged on both ends, which means it's semi-free to move. It's basically, I mean, it's connected, but it's not rigidly inserted and connected and bolted down, right? It's just kind of loosely connected. Maybe there's a clamp here, something to that extent, right? So each of these gives us a different boundary condition, right? Each different end has a different set of conditions. Okay, so depending on what kind of end is being specified is how we sort of set up our boundary conditions for our models. This is going to be the biggest part that you're going to have to watch out for as you go through these examples. Is the math is pretty easy at this point, right? You guys have been solving these kinds of things a lot. What you're going to have to watch out for is, what are my initial and boundary conditions for the different setups, right? So there's only 3 to remember, so it's not that hard, okay? First one is embedded. So if I am embedded, if I'm completely fixed at both ends, I have boundary conditions of y is 0 and y prime is 0. So that means that at the initial condition, y is 0 and y prime is 0, and also at the terminal end, y is 0 and y prime is 0. So this applies to both ends, okay, to both ends. If I am free, these are my conditions, that the second derivative and third derivatives are 0, and again, that is at both ends as well, okay? So again, you're applying these to both sides, or to whichever side is relevant, right? If one side is embedded, you use this. If the other side is free, then you would use this at that side, okay? If I am simply supported or hinged, I have these conditions, okay? So we can mix any of these 3 up. So example, if I'm embedded on one end, I have these conditions on that end. If I am simply hinged on the other, I use this on that side, okay? If I'm free on an end, I use these conditions, okay? And if I'm embedded on the other, I would use these conditions on that end. So we mix and we mix these things where appropriate, okay? So whatever's going on in our system, we choose the appropriate conditions for that boundary, either the initial value boundary or the terminal side boundary, okay? So these things get mixed up It's not just, oh, it looks like this, so this is the only one that I'm using. It depends on which end has which condition, right? So we mix these things up as appropriate, okay? So let's go through an example. I try to choose one that has a mixture of these things so that you can see what I mean. So here's our example. A beam is embedded at its left end, okay? So there's embedding at the left, at the initial, and simply supported at its right, okay? My load per unit length is a fixed constant, W naught, and my X value, right, my beam has a length from 0 to L, okay? So that's how long my beam is. That's basically what this example is saying. So what we're going to do is we're going to find the deflection of a beam of length L that is these conditions on its ends, on its initial end and its terminal end, and has a weight of per unit load weight per unit of a fixed amount, okay? So we know that this is our equation. We have our EI. My WX is fixed, right? It's a constant. It's not variable. My boundary conditions then, okay, so again, I'm embedded, so this will be what's happening at X naught, and then I'm simply supported, so then this is what I'll look like at my boundary, okay? So Y of 0, Y of 0 is 0, Y prime of 0 is 0, Y of L is 0, and Y double prime of L is 0, because this is at the ends and this is at the initial, okay? So Y of 0 is 0, Y prime of 0 is 0, and for the boundary, Y of L is 0, and Y double prime of L is 0, because that is what my boundaries are telling me to do, okay? So if we set this up, so we put it into a standard form, because remember, EI, these are not variable, they are fixed constants as well. So I basically have that the fourth derivative is equal to a constant. Now your book does a couple of cool things. They say that you can pretty much just take this, you can integrate this 4 times to get down to y, and you'll have your equation there, or at least your general equation, which is fine. We can also just use the auxiliary equation, which turns into m4 equals 0 for the general solution, which means that I have a repeated root of 0 4 times. So it's the same thing. It's actually, I think, faster to just do your auxiliary, look at the roots, and then build it up, rather than trying to differentiate this 4 times and, I'm sorry, integrate it 4 times and kind of seeing what happens, right? It's kind of necessary. So we just use our auxiliary equation. Remember, we do that when this is equal to 0. So this is what I have. It's non-homogeneous, so I look at the form. This is a constant, so my general solution, my particular solution should be a constant. But notice that I already have a constant here. So I have to take care of the multiplicity by multiplying it by something, some value of x. In order to get rid of the multiplicity, I can't multiply it by x because I have one of those. I can't do x squared because that's there. I can't use x cubed, so I got to use x4. Okay, so remember, if this shows up already, we have to multiply it to get rid of the multiplicity, because this is a particular solution, this is a general solution. They can't have the same thing going on here. They have to be linearly independent from each other, right? So this is the form of what I have. So if I want to substitute this into my equation, I need to take this derivative 4 times. Okay, so very easy to do. This should be the easiest derivative you probably have ever done, right? So it's just a power function, so I get yp equals 24a. Once I go through my differentiation, it's just a power series, right? So now I set this equal to my function, right? If I'm plugging this in, I get 24a is equal to this constant, right? And I'm trying to solve for a, so I just divide by 24 on both sides. Okay, so my constant of a is w naught over 24 ei. So when I throw that back into my equation, I have this as my particular solution. So when I throw my general solution together with my particular solution, right, my superposition principle, linear combinations, this is what my solution looks like. Now, again, I'm going through this kind of fast because it's pretty basic. This should be one of the easier problems you guys have done. It's just that there's a lot of variables here and not a lot of numbers, right? So, in order for me now to solve this, I have to go back and apply my boundary conditions, right? So if you notice, I have an initial condition with the derivative, and I have a boundary condition with the second derivative. So I need to find at least up to the second derivative here. So I take the first derivative, c1 goes away, this turns into just a constant. I get this, and I get this. So remember, these are constant values, so all you're doing is differentiating this variable part, right? So you should get this for the first derivative. c2 goes away, this x goes away, this turns into 6. Here, 3 over 6 is now 2, and this drops down to power. So this is as far as I have to go with the derivatives. Okay, so now I got to apply my conditions. So if I plug in my first condition, y of 0 is 0. Well, this goes to 0, this goes to 0, this goes to 0, this goes to 0. I'm left with c1 equals 0. Okay, that's nice. Now I apply my second condition to y prime, which is if I plug in 0, I get 0. So again, same thing, 0, 0, 0. I'm left with c2, and that equals 0. Okay, so these, in my equation, in my solution, these first two terms are gone now. I'm now only stuck with these three. Okay, so let's see what happens when we apply our boundary. Now I'm going to plug in L to 0. Again, remember, these two are gone now. So I'll have c3L squared plus c4L squared plus this crazy thing, L to the fourth equals 0. Okay. So if you notice, if we can try to simplify it a little bit, I have a common factor of at least an L squared. So I can pull that out. So really what I'm going to do, I didn't write it here, but just to think about this equals 0. So if I divide both sides by L squared, well, then I really just have this inside part. So it's nice to kind of factor things out if I can, especially if they're a constant. So really what I have is just this thing equals 0. So if you can see, it's in the form of a polynomial, which is nice. I can't factor it right now, so we'll just leave it alone. If I apply L to my second derivative, okay, same thing. Okay, so my second derivative, you see c1 and c2 aren't there already, so that's fine. So I'm going to get 2c3, 6c4L plus my constant over 2 times the flexural rigidity, L squared. So when we plug that in, this is what we have, right? So again, I'm plugging in L everywhere for the second derivative, and that's equal to 0. Okay, so I have this polynomial. So now what I need to do is I have this equals 0 and this equals 0, and that is what I need to solve in order to figure out C3 and C4. So again, I have one equation, two equations, both in terms of the same variable, C3 and C4. That's what I need to solve, not L. L is a fixed constant in this case, right? But I can use these two equations to solve for my two unknowns. I have the same amount of unknowns that I do equations, so I can solve for it using a system. Okay, so I need to solve the system. So if you notice, it's a quadratic and a quadratic. You're not gonna try to solve this and this separately. That's not really what we want to do, because again, if I try to solve this quadratic, I'd be solving for L, right? I don't need to know L, I need to know C3 and C4. So I can set these two things equal to each other and then solve. That's one way of doing it. However you need to solve a system of equations is fine. So I'm going to move on to the next page. So hopefully you guys have copied this down. And we'll just do it by a simple elimination method. But if you have other methods, those of you who are familiar with linear algebra, you can use your linear algebra methods. I suggest that you move this constant, because this is a constant. I know it looks like a polynomial to us because it's a non-L, a single L, and then something squared. but this is not an unknown value. This is whatever the length of our thing is. This is a constant. I have two unknowns plus a constant equals 0. So it's much more easier to move this over and then just have a standard system of equations. Okay, so that's what I'm going to do. I'm going to move one over because it's equal to 0, and I'm going to take the other one and I'm also going to move it over. So now I have my two equations in the same two variables, and then I have the constants on the other side. Again, I had to move them so that they're negative now. Okay, so now the easiest thing for me, instead of trying to solve for 1 and substitute it in, which is fine, you can do that. What I did was I multiplied this by -2. I actually did +2 and I subtracted them. So that's a little bit easier. That'll give you this result. So again, if I multiply this by 2 and I subtract them, these go away. I got 2 minus 6, which is a -4. 2 minus 6 is a -4. And then I'll have this thing here, which I can solve for. So as you can see, I changed my signs because what happens here is that this, you have a very small number minus a larger number. This ends up being positive. So I got the -4 and then I changed the signs as well. Okay, so if you want to take a second to just check that this is the correct value, that's fine. Or if you're using a matrix or any other method, then you'll see that this is also the correct value. So now I have 4c4 times L equals this. So if I really want to get c4 alone, I divide by L. So this will go from an L squared to just an L. And I divide by 4. So this will be -5 over 48. Okay, so c4 is -5. The load constant divided by 48 times the flexural rigidity times the length of our rod. Okay, so again, all of these things are constants. Hopefully by now you guys are familiar with identifying what things are constant values and what things are variables. If you think everything's a variable, then when we start integrating, differentiating, you're going to have a terrible time. So just make sure you're really aware about what variable it is that you're working with. Otherwise, it's very easy to get confused. Okay, so if this is C4, I can come back and I can plug it in somewhere, most likely here. Okay, so if I plug it into here, I have a -5 W0 L 48 EI times another L, so that gives me an L squared times this thing, and then I can it'll be negative, so I can add it to both sides. So basically what I'm doing is all of these are the same. I'm really just adding -1 over 24 plus 5 over 48. So in order to get these denominators to match, this doubles. So this is really going to be -2 plus 5, right? -2 plus 5. So, sorry, L squared, so -5 over 48. So in order to get this to double, -2, yeah, so I'm going to have, 3 over 48 is what I'll end up doing. 3 and 48 simplify to 16. So I got C3 is 1 over 16 W0 EI over L squared. Okay, so if you got to write out more than that, that's fine. Okay, but again, fractions don't go away, so get real comfortable with those things. We're actually going to be doing a lot of fractions pretty soon. So make sure you brush up on your fractions because they are going to be everywhere in chapter 6. Okay, like everywhere. Just a heads up. But chapter 6 is actually my favorite, so we'll have some fun when we get there. Anyways, so this is what we have. So now I have C4 and C3. If I go back to my equation, which you guys should have readily available, this is what I have here. C1 and C2 are gone. Now I have C3 and C4, and this is just a constant, right? So when I plug those in, this is my solution. Okay, now you're fine with keeping it like this, that's fine. Okay, however, a lot of times it seems that these things simplify pretty well. So notice that I have denominators that are very similar. All of these things are multiples of 8. I can pull out a 1/8 W0 EI x squared minimum. but then that's going to leave me with fractions inside of my parentheses that I'm factoring out of. So instead, let's pull out the common denominator, and then what that will do is that'll leave us with whole numbers on the inside. Okay, so if I pull out 48, all of these have things that are in common with 48. So if I pull out 48, this will be left with 5. If I pull out a 48, this will bump up to a 3. If I pull this out as a 48, this will bump up to a 2. Okay, so I'm pulling out a factor, so anything that's less than 48, there will be a multiple on top of. Okay, so what do I mean by that? I mean this, right? So again, if I were to distribute this, I'd have 3 over 48, which is 1 over 16. 5 over 48. 2 over 48 is 1 over 24. Okay, so I'm just pulling out this constant so that I have a nice polynomial on the inside, and I'm pulling out the greatest common factor of x's that I have. So I'm left with this polynomial-ish thing. Remember, L's here are constants. Okay, but this is actually factorable as well. Okay, so I can factor this to L minus 2x times 3L plus x. Right, and so that is my solution. Okay, now we're going to move on to our next sort of equation that we're going to work with. These are eigenvalues and eigenfunctions. Okay, now these have the form of y double prime plus some constant times y equals 0. And then these are our boundary conditions. So y of 0 is 0, and at the boundary we are also going to be 0. Okay. Here lambda is called the eigenvalue of our function. Okay. So there's 3 cases. So we've actually looked at this before. We're going to look at this a little bit differently. Okay. In the last section we considered some of the things that look like this. I think in fact our first equation had this kind of form when we were talking about the mass on a spring with no velocity dampening and just straight free motion. It was a second derivative plus a constant times our position equation, right? So here let's assume that lambda is 0. If lambda is 0, I get y double prime is equal to 0. Okay. This gives an auxiliary equation of m squared is 0, very similar to what we just did. In the last one we had m4 was 0, so we have 2 zeros, which are 0. Repeated root, so then we get a constant, and then the x in order to keep us from having linear dependence, right? Keeping them linearly independent of each other. So let's explore this. Let's apply these boundary conditions to what our solution would look like here. Okay, so y of 0 is 0 for this means that this goes to 0, and I'm left with c1, which will be equal to 0. Okay, when I apply my boundary condition, I get well, this is 0, so I get c2l is 0. And the only way for that to happen is if c2 is 0, because I have an actual length that's not, you know, I have a length of a rod of something, right? So the only way for this to work is if this constant is 0, which means that for this equation with these conditions, the only solution is the trivial solution. Okay, so now let's look at the second case. Okay, the second case is that this eigenvalue is negative. Okay, so if this eigenvalue is negative, then I have this as my solution. So when I go to solve my auxiliary equation, the negative value when I move it over will be positive. So I could write this as the square root of negative lambda, because again it's negative, so the negative of the negative would be positive. But it's very confusing because you'll see the negative sign here and you'll think that it's negative when it's actually positive because it's the negative of a negative. So the easier thing to do is for me to just write it as an absolute value, because it's easy to tell that the absolute value of this thing is positive. Okay, so I'm just going to keep this notation. I'm not going to write square root of the negative lambda because again we're going to want to pull out the imaginary value that does not actually exist there. Okay, so if this is negative, once I move it over it's actually positive, so that's why I'm taking this absolute value. It's just there to remind us that it's actually being positive it's positive at this point. Okay, so if this is my solution, I have actual solutions, positive and minus. So my equation will have an answer that looks like this: a constant times e to the x times that value plus c2 e to the negative x times this value as well, right? So again, one's positive, one's negative, so it's keeping them linearly independent. Applying our boundary conditions, I have y of 0 gives me 0, so this goes away and this goes away. That leaves me with basically c1 is the same as c2, or c1 plus c2 is 0, so move 1 to the other side, we have c1 is negative c2. If I apply my boundary condition, y of L is 0, I will have 0 is, instead of x is everywhere, L's. So again, remember these are constant now. Okay, so that doesn't help me a lot. I don't really have enough information to solve for my C1 or C2. I do have two equations. I guess I can solve for these because they are, I have two equations that are equal to 0 with only two unknowns. But let's look at this. Let's say that C1 was 1/2. Okay, C1 was 1/2. Then I would have this, right? Remember C2 was the opposite sign. This is the same as sinh, okay? Where the exponent is our value here, okay? So you might not remember sinh too well, but it's a lot easier to write this as a single value that we understand how to work with rather than a linear combination of functions, okay? So again, I'm assuming C1 is 1/2, but we don't actually know what it is. So I can call it 1/2 times something else. Okay, so since I don't know what C1 is, I can rename C1 as 1/2 times the original value of whatever C1 would need to be. So basically what I'm getting at is C1 isn't actually 12. I'm sorry, 1/2. But if I take 1/2 times something, it's a constant. Right? It's an unknown constant, just like when I call it just C and then we do some stuff and I just leave it as C, even though it's not the same exact values before. It's the same thing. I'm just using C1 because it's easy to refer to. Okay, so we can call this C1 sinh of this. That'll just make it a lot easier for us to work with. If you guys are familiar with this, this will never be 0. Okay, I will never have 0 out from sinh. Sinh is a linear combination of exponentials. It's never 0. Okay, the only way for this to be 0 is if the constant that is attached to it is 0, and that's not going to happen. Or if that happens, then we have the trivial solution. Okay, so if lambda is negative, then the only solution that we're going to have also is the trivial solution. All right, so let's look at our last case. So just as a refresher, from case 1 and case 2, both of those conditions led us only to the trivial solution. Okay, so for case 3 is that we are larger than 0 for that constant value in our equation. So this gives us an auxiliary equation of m squared plus lambda is 0. So now when I move this over, now that it's positive, I can play around with it like you would expect it to be. So when I move it around, I will get a negative. So when I take the square root of both sides, I get an imaginary square root. Okay, so we know what this looks like when you plug it into your general form of an equation. We get the sines and cosines. There's no real part here, so there's no e to the real part exponent attached. Okay, so now what we're going to do is the same thing we did before. We're going to apply those boundary conditions. So the first one is the one at the initial value. So when I plug in 0, sine of 0 goes away, so I'm left with 0 is equal to C1. Okay, because this is 1, C1 equals 0, so that's my answer. When I apply my boundary, I'm going to have similar to the sinh, but it's going to be sine. Okay, so sinh is never 0, but sine is. So I got 0 is C2 sine L to the square root of, sorry, this should be lambda. I guess I messed up here. Okay, so this should be L square root of lambda. Okay, so these ones got mixed up, but this is a lambda. I'll fix that in the write-up. Pretty good. We're 35 minutes in, and that's my first mistake, so getting a little better. So this is going to be true whenever L times lambda is equal to a multiple of pi. Okay, remember sign is 0 whenever not at 0 but at pi, at 0, pi, 2 pi, 3 pi, 4 pi, 6 pi. So whenever we have a constant multiple of 0, okay, so here n is a part of the positive integers, right? Z is the integers, the plus here makes it the positive. So this is the positive integers. So whenever this is 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 20 pi, whatever, this will be 0. Okay, so whenever this part, okay, this L lambda, again, this should be lambda, not an x. Whenever L times lambda is a multiple of pi, we get out 0. Okay, so in other words, if my original lambda value is n pi over L squared, so really what I did was I just took this and I solved for lambda, so divide by L, then square both sides. Okay, so if lambda is equal to this, then y equals C2 sine n pi L over x is a non-trivial solution. That's the only time. Okay, if this is not true, then I have only the trivial solution. So this is the only time when we have solutions here. Okay, this is a very, 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 very important result. This pops up a lot. Okay, you're not going to see it a lot in this class for the remainder of the course. It will pop up, but not a lot. But when you study PDEs, partial differential equations, so when you take your next differential equations course, and you will take another differential equations course for my engineers and physicists, this is not the last one, right? This is a very, very important result, and it shows up a lot in partial differential equations. In fact, this is the main portion of a solution for a Fourier series solution. Okay, so when we get to chapter 6, we may talk about the Fourier series solutions. Probably not, because they're pretty much reserved only for PDEs. Not only for PDEs, but they're meant for PDEs. But this is a very, very, very important term that pops up in Fourier analysis. Okay, so this idea right here is just one single little line, one little case from a small sort of derivation that we're doing, but it has a lot of implications. This is very, very important. Again, I cannot stress this enough. This is a very foundational sort of result that we have here. Okay, so anyways, again, notice that n can take on an infinite number of values, so these come in what we call modes, right? So the solutions show up in modes, and those modes are whenever you have a constant multiple here. Okay, so let's look at how this is applied to some other things, okay, to some applications. So we have two examples. We're going to go through these kind of fast. We have the buckling of a thin vertical column. So basically what happens is we have a long thin column of length L. Y of x is the deflection at a point x along the column when a load P is placed on top. So again, this is very, very similar to the first example that we did, which was the deflection in a beam, right? Here we're just, it's not a beam, it's just a very thin kind of rod or string or something, right? So the equation we have here to model this is the flexural rigidity times the second derivative plus this load that's placed on top. Okay, for the other one, the load can be placed sort of along the center of a beam. Here we are explicitly saying it's on top. Okay, so if I put this into standard order, I get y double prime plus p over the flexural rigidity of y equals 0. And if you notice, this is in the form that we just looked at, okay, which is the eigenvalue form. So note that this equation is in the form y double prime plus y of lambda y equals 0, where my lambda is this constant, right? This is the exact case we're just looking at. So the only solutions that we have here are when this happens, when this is positive, which it will be, right? Because the load we place is a positive value, is not a negative load, and the flexural rigidity is going to be positive, right? So this will be a positive value, so that gives us case 3. Okay, Now what we have to be concerned with is the boundary conditions. And our boundary conditions will match up if we are simply supported. Okay. So this is our picture from the book. So again, I have a very thin vertical column of something, and I'm placing some pressure on top. Here, the axis of symmetry is the vertical axis, so then it's going to bend in the y direction, either this way or that way. We'll just call this way positive. Okay, and as we put pressure, it'll continue to bend. Think about a thin ruler. If you put it between your hands and then you start to press your hands together, the ruler was going to bend, right? Or even a piece of paper or anything like that. So that's basically what we're studying here, right? Putting pressure along the axis of symmetry to get this this bending moment, right? So for the solution for the different values of Pn, so this is what our solutions will look like, okay? These are called the critical loads, and they correspond to the number of nodes that will lead to failure under our pressure Pn, okay? The first node is called the Euler load. So if you are in physics or engineering again, and you've studied vibrations on a string, very, very similar, okay? So here we have one node, here there are two, here there are three. So if you notice, if you put weight here, it is going to buckle because there's not a lot of support here, right? There's weakness at a very specific sort of in a specific manner, right? Now if this was offset, okay, if there was not a node here, then I would be stronger here. This is the first sort of what we call buckling state, okay? Did I write that? This is the first buckling position. This would be the second. This would be the third. Then we would have a fourth, and more and more and more so, right? So it gets weak because there's not a lot of strength here, right? So the next thing we can talk about is a rotating string, okay? That's going to be very similar to this example, okay? If we were to rotate a string. Here we're not rotating anything. Here something is just buckling under pressure. But if we look at the rotation of a string, it looks very similar to this shape. It just has some angular momentum to it, okay? So let's say that two people are playing jump rope. So we can say that two ends of a string are embedded in that case because both ends are being held at a fixed position. Y of x is going to be the deflection from the axis of symmetry at a point x. Okay, same thing as what we've been talking about as before. So in other words, the solution is just going to be the shape of the curve of the rope, right? So if we look at a small portion of our rope, okay, from let's say x to delta x is a small increment, okay, then our net vertical force is F equals T2 sine of theta over 2, or theta 2 minus T1 sine of theta 1. So let's look at what this picture is, and then we can talk about this in a second, right? Here, each Ti is the magnitude of the vector attached to the angle. Okay, so again, we have this curve of our rope. Okay, my curve continues this way. So if I'm looking just from here to here, this is x, and this is a little bit more than x. Okay, this T2 is the tangent vector. Okay, it's the vector that's continuing on in this case. If I talk about the difference from one point on the rope down to where I start my tangent vector, I create an angle of theta, okay, either theta 1 or theta 2. Okay, so for this side, theta 2, this top part right here is sine of the angle times the length of the vector, right? So remember, this is not a unit circle. This is something of a radius of length T2, or the magnitude of T here. So this vertical length is the length, the radius, right? The length of this vector times the sine of the angle. Same thing here. It's going downwards. So from this point to here, this vertical length is going to be the length of this vector, the magnitude of this vector, okay, times the sine of this angle. So that gives me this sine and this sine, right? This vertical length and this vertical length. So this length plus this length is the total vertical difference, or the vertical force, the up and down force, right? So this is coming from, right? So this comes from the idea of the resultant force of vectors, right? So adding their components and getting the resultant force. So this is the resultant vertical force. So, or in other words, the net vertical force. Okay. So that's where this formula comes from. It's just talking about the force in the vertical direction. Okay. So we're looking at the signs of the two sides with vectors of length t1 and t2. Here we're going to assume that t1 and t2 are the same length. Okay. Now when these angles are small, okay, the tangent is basically the same thing as the derivative. Okay. So the tangent vector here is basically the same as the magnitude of this vector, and the tangent vector here is the same as the derivative here, right? That's what a tangent vector is. So that's all this is saying. Okay, the tangent, when these things are small, the tangent vector, the tangent value is approximately the same as the derivative at the endpoint for 0, 2. Okay, 0, 2, or theta 2 is at x plus delta x. Theta 1 is at x. Okay, so that's it. We're just saying at theta 2, this is the derivative at that point. At theta 1, this is the derivative of that point. Okay, so then when we put these together, okay, since the tangents are the same, we get that this force is the same as the difference between these. Since t1 and t2 are basically the same, we're basically just pulling that out. We're equating those values here. Okay. So another way to derive f is to note that f is the same as mass times acceleration, which is equivalent. I should take out this equal sign. It is approximately the same as negative rho delta x times r times omega squared. Okay. Here rho is the mass per unit length along delta x. The radius is the distance up, and then omega squared is the angular speed. Okay, so let's kind of just summarize that up. Rho is the mass of the rope. Rw squared is the angular speed with radius r. And the force points down, which is why this is negative. Okay, so this is what we have. So here it should be very clear that r is actually just our y value. Okay, at any point along here, we have different radii. So that's given by that deflection curve function. So again, you don't have to memorize all this. This is just helping us to derive. They're never going to say, hey, this is your rho. Hey, here is your, find the angular speed. You're just going to have to solve the equation. We're just using this to help derive our equations. Okay. So my force is approximately the same as negative rho delta x times y times omega squared. And if I set these two things equal to each other, this is the equation that I have. Looks like I'm missing a parentheses here. I'll add that in the write-up. We know that this is the rate of change if I divide by delta x here. Okay, that is our difference quotient, and the difference quotient for a small change, as that change goes to 0, is really just the next derivative. So this is just the second derivative. Okay, so remember this delta x divided on this side so that we can turn that into the second derivative. And if I add this stuff over, I have this as my differential equation. And if I divide by t, now I have an eigenvalue sort of system, right? So this is in the form that we studied a couple of minutes ago, where this lambda value, right, this eigenvalue is rho times omega squared over t, right, the length, the magnitude of our vectors. Okay, so your classwork is to basically derive your solution for this system. So again, you're really just doing what I did earlier for the lambda case. You're just going to put that into that form and then find the critical speeds omega n for the corresponding deflection. So basically you're going to look at those different nodes, right? So the different values of n n is 1, n is 2, n is 3, n is 3, 4, etc. And then what do the corresponding solutions look like for your different sort of nodes that you have. Okay, so I'll put up a link so that you can submit this classwork. It really should not be that long, right? I've already went through the derivation for you, so you're just kind of repeating the same thing, but for this case. Okay, so I'll post that up, and that'll be due tonight at midnight. Thanks, guys.